Okay, so the eigenspace associated to an eigenvalue is the null space of A minus lambda times the identity. And to say that a vector is an eigenvector of a matrix is to say that it satisfies the equation A times V equals lambda times V. So a question we can ask now is, well, where do we find all of the eigenvectors? And this is actually a question that we answered a while ago when we studied bases for null spaces. So let's flesh out how the theory comes together here. The first new vocabulary word here is the geometric multiplicity of an eigenvalue. So we define the geometric multiplicity of an eigenvalue notationally as maybe gm sub a of lambda, and by definition, the geometric multiplicity is equal to the dimension of the eigenspace associated to the eigenvalue. Now, one observation to make here is that, well, by definition, the geometric multiplicity is the dimension of the eigenspace, but the eigenspace is equal to the null space of A minus lambda I. And one thing we know about the dimension of any null space is that it is equal to the nullity of the matrix in question. So the geometric multiplicity of an eigenvalue is the same thing as the nullity of A minus lambda times the identity. And of course, one thing we know about geometric multiplicity, therefore, is that at minimum it has to equal 1, because by definition, to say that lambda is an eigenvalue is to say that A minus lambda times the identity is a singular matrix and therefore has minimum nullity equal to 1. So what sorts of things can we say about geometric multiplicities? Our first non-trivial, yet an incredibly important fact about geometric multiplicities is the following. Let's say that we manage to find all of the eigenvalues of a matrix. It turns out that if we sum all of the geometric multiplicities of all of the eigenvalues, we will never get a number larger than the size of the matrix. So if A is an n by n matrix, and we sum up all of the geometric multiplicities of the eigenvalues, we never get a number larger than n. And of course, one consequence of this theorem is this puts a bound on the number of eigenvalues that a matrix can have. So an n by n matrix can never have more than n eigenvalues. We'll find that an n by n matrix might have fewer than n eigenvalues, but it never has more. So here's an example. So here we have a nasty 3 by 3 matrix, and I managed to find the eigenvalues of this matrix. I found that this matrix has exactly 2 eigenvalues. One of them is lambda equals -2, and the other is lambda equals 5. Let's look at the geometric multiplicities of these eigenvalues. So remember, by definition, the geometric multiplicity of an eigenvalue is the dimension of the corresponding eigenspace, and by definition, that eigenspace is the null space of the difference matrix, and that null space has dimension equal to the nullity. So if the first eigenvalue here is lambda equals -2, then our first geometric multiplicity is the geometric multiplicity of -2 as an eigenvalue of this matrix. And what we want to do to calculate this number is look at the difference between A and -2 times the identity and figure out the nullity of that matrix. Well, how do we figure this out? Well, what we need to do is we need to go to this 3 by 3 matrix and subtract -2, which is the same thing as adding 2, to each diagonal entry of this matrix. So -30 becomes -28, 119 becomes 121, and -81 becomes -79. So we want to know the nullity of this matrix. And one thing to point out is we actually know a few things about the nullity here. So first of all, the rank of this difference matrix cannot be equal to 0 because this is not the 0 matrix. We also know that it's not equal to 1 because the columns of this matrix are not multiples of each other. To get the third column from the first, we would have to multiply it by 1, so -28 can remain -28. but 71 is not equal to 57. So we know this rank is not equal to 1. We also know that the rank is not equal to 3. Why is the rank not equal to 3? Well, by definition, we are told here that -2 is an eigenvalue, and by definition, to be an eigenvalue means that this difference matrix cannot have full rank. So once we've eliminated 0, 1, and 3 from the possible ranks here, that tells me that the rank has to equal 2. So let's just walk through that logic one more time. A minus -2 times the identity is equal to this matrix. We're studying this matrix because we're told -2 is an eigenvalue of this matrix A. Well, we know, since this is an eigenvalue, that we must be dealing with a singular matrix. Yet we know that the rank is not 0 because this is not the 0 matrix. And we know that the rank is not 1 because the columns aren't all multiples of each other. Well, if this is a singular matrix, then the rank is also not equal to 3, so the only option is for the rank to equal 2 here. And if the rank of this matrix, this 3 by 3 matrix, is equal to 2, that means that the nullity is equal to 1. So this is our first geometric multiplicity calculation. The geometric multiplicity of -2 as an eigenvalue of this matrix is equal to 1 here. Let's look at the geometric multiplicity of 5 as an eigenvalue. By definition, the geometric multiplicity of this eigenvalue is the nullity of the difference matrix. So now we want to look at this matrix A minus 5 times the identity matrix and calculate its nullity. Well, we're now subtracting 5 from the diagonal of our original matrix here. So -30 becomes -35. 119 becomes 114. And -81 becomes -86. So now, again, we're looking at the nullity of this matrix. Well, we know a few things about the rank here. Again, the rank is not 0 because this is not the 0 matrix. The rank is also not equal to 1 here because these columns are not all multiples of each other. And again, we know that the rank is not equal to 3 because 5 is an eigenvalue, so this difference matrix cannot have full rank. So this once again forces the rank to be equal to 2, and a 3 by 3 matrix with rank equal to 2 has to have nullity equal to 1. So in this example, we have a 3 by 3 matrix with 2 eigenvalues that have been handed to us, and we just calculated both of the geometric multiplicities. In this example, both geometric multiplicities are equal to 1. And this is compatible with the theorem we just stated, because we just stated that if we sum all of the geometric multiplicities of the eigenvalues of a matrix, then we never get a number that exceeds the size of the matrix, but we might get a number smaller than the size of the matrix. In this case, when we sum the geometric multiplicities, well, there are 2 of them, and they're both equal to 1, and 1 plus 1 is 2, which is smaller than the size of this matrix, which is a 3 by 3. Here we have a different 3 by 3 example. Here we have another 3 by 3A, and someone has gone to the trouble of finding all of the eigenvalues of this matrix. It turns out that the eigenvalues of this 3 by 3 are the numbers lambda equals -1 and lambda equals 4. Let's calculate the geometric multiplicities again, or let's do another geometric multiplicity calculation. The geometric multiplicity of -1 as an eigenvalue of this matrix is the nullity of A minus -1 times the identity. Well, if we subtract -1 from the diagonal of this matrix, 4, that's the same thing as adding 1 to the diagonal. So 4 becomes 5, 19 becomes 20, and -21 becomes -20. This is an interesting matrix. So if we look at this difference matrix, we find something kind of interesting. To get the second column from the first column, we can actually accomplish that by multiplying the first column by -4. We can also get the last column from the first column by also multiplying by -4. So this is equal to a rank 1 matrix. And any rank 1 matrix that's 3 by 3 has to have nullity equal to 2. So we just calculated the geometric multiplicity of -1 as an eigenvalue. The geometric multiplicity of -1 as an eigenvalue of this matrix is equal to 2. What about the geometric multiplicity of 4 as an eigenvalue? Well, now we're looking at the nullity of A minus 4 times the identity matrix. Well, we need to now subtract 4 from the diagonal of our original A. 4 minus 4 is 0, 19 minus 4 is 15, and -21 minus 4 is -25. So now we're interested in the nullity of this matrix. This matrix is clearly not rank 1, because if it were, every column would be a multiple of this first column, so the first entry in every column would have to be 0, which doesn't work here. So this is not a rank 1 matrix. It's certainly not a rank 0 matrix. And it can't be a rank 3 matrix because we know that this difference matrix must be singular because we're told that 4 is an eigenvalue. So we can eliminate 0, 1, and 3 from the possibilities of the rank in this instance. So that forces the rank to be 2, and any 3 by 3 matrix with rank 2 automatically has nullity equal to 1. So this example differs from the previous example in the sense that we still have a 3 by 3 that has 2 eigenvalues, but now if we sum the geometric multiplicities, we achieve the size of the matrix. So 2 plus 1 is 3, and this is a 3 by 3. In the previous example, the two geometric multiplicities were both equal to 1, and 1 plus 1 was 2, which was less than the size of the matrix. Here we have yet another example. So here we have another 3 by 3 matrix, and someone again has gone to the trouble of finding all of the eigenvalues. In this example, our 3 by 3 matrix has 3 eigenvalues, and those are -2, 1, and 7. Well, remember that at minimum, every geometric multiplicity is equal to 1, and it might be bigger. But we also know that when we sum the geometric multiplicities, we can never get a number larger than the size of the matrix. So that actually forces the sum of all of these geometric multiplicities to equal 3 in this example, which forces each of the geometric multiplicities to equal 1 in this example. So because we have a 3 by 3 with 3 eigenvalues, each of the geometric multiplicities is forced to equal 1. Okay, so now let's talk about finding bases for eigenspaces. So the first thing to point out here is that it is easy to verify whether or not a given vector is an eigenvector of a matrix. If we're asked whether or not a vector v is an eigenvector of a matrix A, we need only check the equation A times v equals lambda times v. So here we have an example where we have the same matrix A and we're multiplying by 2 different vectors. So we're taking this 3 by 3A and we're multiplying by the vector -3, -2, 1. And the result of this multiplication is 6, 4, -2. The thing to notice here is that A times this particular vector happens to equal -2 times this particular vector. This one matrix vector multiplication tells us that V is an eigenvector of A, and its associated eigenvalue is -2. So it's appropriate here to write V belongs to the eigenspace of A, where the eigenvalue is -2. On the other hand, we have this calculation where we take A and we multiply it by the vector W, whose entries are -4, -4, 5. And the output of this matrix vector multiplication is 5, 3, -1. Well, one thing to note here is that 5, 3, -1 is certainly not a multiple of -4, -4, 5. What this means is that the vector W is not an eigenvector of the matrix A. So just as in the theory of null spaces, when we want to verify whether or not a vector is in the null space of a matrix, we just have to check a simple equation. Does that vector when multiplied by A, produce the 0 vector? Same goes for eigenvectors. If someone gives us a vector and we want to know whether or not it's in an eigenspace, we simply check whether or not A multiplied by that vector is lambda times that vector. But a more sophisticated question asks, well, how do we produce eigenvectors? So where do the eigenvectors come from? So on one hand, we have the verification problem, which we just illustrated to be easy. But on the other hand, we have the production problem. How do we find eigenvectors? And we already know the answer to this question because we know how to work with null spaces. If someone asks us to find all eigenvectors, what they are really asking is for us to find a basis of each eigenspace. And since eigenspaces are defined as null spaces, and since we know how to find bases for null spaces, we know how to find bases for eigenspaces. So each eigenspace is the null space of A minus lambda times the identity. So finding a basis for the space is not a new project for us. So let's see this with an example. So here we have a 3x3 matrix, and someone has gone to the trouble of finding all of the eigenvalues, and there are two of them here. Lambda equals 3 and lambda equals -2. So how do we find bases for eigenspaces? Well, this matrix will have two eigenspaces, one for lambda equals 3 and another for lambda equals -2. By definition, the eigenspace for lambda equals 3 is the null space of A minus 3 times the identity matrix. Well, A minus 3 times the identity matrix can be found by subtracting 3 from each diagonal entry in this matrix. So 8 becomes 5, -2 becomes -5, and -2 becomes -5. So now we're looking at the null space of this difference matrix, and we can find a basis by looking at its reduced row echelon form. Here what we're finding is this difference matrix has rank 1, and the second column is -1 times the first, and the third column is equal to the first column. So in the reduced row echelon form, the first row is 1, -1, 1, and every other row is equal to 0. For lambda equals -2, well, we want to look at A minus -2 times the identity, which is the same as A plus 2 times the identity. So now we're adding 2 to each diagonal entry. 8 plus 2 is 10, -2 plus 2 is 0, and -2 plus 2 is 0. When we calculate the reduced row echelon form here, we get something a little bit more sophisticated. We get a rank 2 matrix, and the columns are 1, 0, 0, 0, 1, 0, and then 1, 1, 0. So now, to find bases for these eigenspaces, all we need to do is use these two reduced row echelon forms to find the general solution to difference matrix times x equals the 0 vector. This first geometric multiplicity, which is the dimension of our eigenspace, well, that's the nullity of the difference matrix, which for lambda equals 3 is equal to 2. So we should end up with two basis vectors for the eigenspace with lambda equals 3. And we found that our difference matrix A minus -2 times the identity is a rank 2 matrix, which means it has nullity 1, which means we should end up with one basis vector. So the geometric multiplicity for lambda equals 3 here is 2, whereas the geometric multiplicity for -2 is equal to 1. When we use these reduced row echelon forms to find bases, we end up with two basis vectors for our first eigenspace, 1, 1, 0, and then -1, 0, 1, and then we get one basis vector for our second eigenspace, -1, -1,